I'm Cindy Kelly. It's Monday, February 6, 2017, in Santa Fe, New Mexico, and I have James L. Smith. My first question to him is to say his full name and spell it.
James Lawrence Smith, James Lawrencesmith.
Great, thank you. Why don't you begin by just telling us a little bit about yourself and what your background is, where you went to, what you studied and so forth, where you were born. It's in a nutshell.
But I was born in Detroit in 1943, the same year that Los Alamos National Lab was founded. I was educated in the Detroit public schools, which at the time were excellent school. It was the finest school system in the country because of the production from the weapons, from munitions for World War II, and for the baby boomers buying cars and appliances, and it was a terrific school system. Then I went to Wayne State University, that's also in Detroit, and then I started on engineering. I switched to physics because they wouldn't let me take enough French. So I switched to a liberal arts program and became a physicist. There were 3 physicists in the faculty who got their PhDs at Brown University, and the 3 of them got me to go to Brown University. They got me a fellowship. So I went off to Brown in 1965 and got my PhD. In the summer of '69, the job market for physicists dried up, and there were no jobs. And I could tell the difference between people who got a job before that summer and after. And so it took a couple of years to find a job, and so I just stayed as a graduate student. And then I got an offer from Los Alamos, and I had done that by sending in an application. They were hiring so little at Los Alamos, they didn't bother to interview. But I submitted an application, and I had some particular skills at low temperature physics that were unusual. I built a thing called a dilution refrigerator, and somebody at Los Alamos wanted me to cool plutonium down to lower temperatures than it had ever been, plutonium metal. And because of its radiation, it puts out heat, and so it's tricky. And on the phone, I told them I knew how to cool plutonium. You do that.
And
you cool it by making electrical contact, and the electrons running across a metal interface will get the heat out. If you try to cool it by submerging it in a cold liquid, it won't cool. It will just heat. Anyway, so I did get plutonium down below 1/10 of a degree Kelvin. And
so how many years were you at Los Alamos?
well, anyway, I came in 1973, and I still have a badge, but I retired on D-Day, on the 70th anniversary of D-Day. It was a Friday. I finally picked that day as a historic day. So I retired on June 6th, 2014, but I still go to work almost every day. And I spend most of my time talking to young people.
That's great. So what we'd like to do is kind of pick your brain about the innovations of Los Alamos, which really, were essential to the success of the Manhattan Project, since it was all brand new.
The innovation at Los Alamos during the Manhattan Project, there were some. They had to do nuclear physics. You had to know the cross sections of all kinds of atoms and things. The theorists had been pretty good at figuring this out. They could guess that plutonium-239 would be a proper nucleus for a nuclear weapon, and it simply had to be confirmed. And it was demonstrated with Glenn Seaborg and others at the accelerators at what is now Lawrence Berkeley Lab, E.O. Lawrence's accelerators, and they sent these things to the University of Chicago to be analyzed, and it was seen that plutonium, it became clear that there were 2 isotopes that you could use for nuclear weapons. Uranium-235, which is difficult to separate from natural uranium because it's around 0.3% fissionable, and then you could produce plutonium-239 in a nuclear reactor. That's what they demonstrated at Stagg Field, whenever that was, at December 1942. 42. I knew two people who were there, Herb Anderson and Harold Agnew. Other theorists like Edward Teller weren't there. Edward Teller never wanted to watch an experiment. He just wanted to hear about it and sit and think. Then they realized that the impurities from plutonium-241 in the reactor fuel would prevent the artillery shell assembly for a nuclear weapon that would work on U-235, and so they had to invent a way to compress metals to truly extreme densities with shaped explosives. And that was one of the things done at the Manhattan Project. I mean, it's interesting how those have evolved since. But this idea that you could take a hemisphere of plutonium and blow it inward to get the density, because you'd think of explosives as ripping things apart. And the idea that you could selectively do that was most interesting. And it's also true that the word computer didn't exist then. They had women doing calculations with hand machines during the Manhattan Project. I mean, they also got the first things from International Business Machine, IBM. But these weren't really computing, they were sorting and doing rather simple things. And there was nothing in the sense of a modern computer. But those women doing those calculations, they called them computers during the Manhattan Project. It was shortly after that people like John von Neumann, and whom I never met, and Nick Metropolis, whom I knew, did get together and make those first machines that would respond to programming and things, and they were called Maniac and ENIAC, and I'm not good at those. And then my friend Paul Stein and Nick Metropolis, first people to play chess with a computer, and they, in order to make the problem mathematically simpler, they used a 6x6 chessboard. They eliminated the bishops, and they called it secular chess. It amused them that they had removed religion from the game of chess. And there are a lot of pictures of them. Oh, the other thing is that some of those photos, Paul Stein was always smoking a Lucky Strike, but in some of the lab pictures, they've airbrushed the smoking out of that picture. Nick never smoked. That was computation. One of the things that is less obvious is why we got into biology. I hope to get back to this. Los Alamos is a multidisciplinary lab. We kind of touch on everything in science. And there were people, even during the Manhattan Project, worrying about the effects. We knew that a nuclear weapon would kill people from the explosion, but there were questions of the radiation effects on human beings. And Los Alamos always has had people doing that. And that, I mean, for example, we had beagles. Beagles have lungs not too dissimilar from human lungs. And we had done, in a building that's still up in Los Alamos, they had beagles, and they studied the effects of plutonium in their lungs and deduced that if the particle size is small enough for the plutonium, that it leads to lung cancer. If the particle size is bigger, it doesn't. There was a guy named Vern Strubing who cast the plutonium for the Trinity shot and what he called in his notebooks the combat shot, and he worked for me for 5 years before he retired in 1979. And he had what was called one body burden of plutonium in his lungs. It was 3 micrograms of plutonium-239, and in time they could measure from the radiation and from density measurements of his lungs how much he had. That was why he got to work for me, when they finally saw that he had what is called one body burden. The body burden, according to the Atomic Energy Commission at the time, was the amount of plutonium you could have that did not cause cancer. But anyway, when they realized that he had one body burden, they let him work for me because I was working on things like uranium and neptunium. They didn't worry about the additive things. They just said if he's not working on plutonium, he'll be safe. But it's okay if he gets uranium and neptunium in his lungs, so he worked for me. he said he wasn't an epileptic, but every now and then he would lie on the floor, and as far as I could tell, he would have an epileptic fit, and that had barred him from military service during the war, and that's why he would go to Los Alamos. He'd been an undergraduate chemist, and he had been anxious to serve in the military, but he couldn't because of what he said wasn't epilepsy, but he did get the plutonium in his lungs, and he was proud of it. He very proudly felt that that was his service for the war. Gee, he also was the guy who made the plutonium for the Trinity shot and the shot on Nagasaki. And he had accepted in the 50s $100 to turn his body over to the lab so they could study his lungs. And when he finally died in 1980, only a year after he retired, I knew how proud he was of the plutonium in his lungs. And his wife had called the division leader, a guy named George Bolts, and said that Vern had died, and and George had reassured Vern's wife that they knew why he died. He had heart problems, and they didn't really want his body. And then I had to intervene. And I got a hold of the funeral home in Santa Fe that had his body, and I said, don't embalm it, to give me some time here. And then I yelled at George Bolts. I was still in my 30s, and it was unusual for me to yell at a rather well-known person at Los Alamos, but I said that Vern wanted his body to go to science. And then the lab did send someone down to take his lungs and a couple other organs so they could track it. In a way, they didn't need it. Oh, and it did turn out that Vern didn't have lung cancer. The particle size of the plutonium was large enough that he was never going to have lung cancer. And in general, the people who worked on plutonium, the 100 or so subjects in the Manhattan Project with doses of plutonium, they have died of lung cancer far below the normal rate. Only the ones who smoked have died of lung cancer. Vern never smoked. But anyway, the laboratory cared about the effects of radiation, and we had these programs. We had the programs with the Beagles that studied lung cancer. But it's the nature of a laboratory that tries to do all sorts of things in science. It was probably in the late 70s, I had a friend named Dick Keller who worked in the same building I did, who did molecular beams, and he had learned how to you deliver up with a little ionization and some acceleration, and he could make a molecule go by and then probe it with a laser, and he could determine what it was. He could measure a single molecule to know what structure it had. My friend Dick Keller was at this party where I met the research MD whose name I forget. It could be tracked down. He moved on. But he explained that you could measure the DNA a molecule at a time, that his enzymes could peel things off, and that you finally had the potential. We knew from the work of Watson and Crick that life as we know it comes from the genome, from the DNA, and we finally had a way to map it, which in fact required to look at a molecule and know what it is. And they convinced, I believe it was around $10 million, they got the Department of Energy to give them enough money to begin this. And in the beginning they would say, gee, we can measure the human genome, but it'll take, I don't know, maybe 100 years. And the number kept going down. And nowadays we can put it into a machine. This is the progress of science. And by the way, Los Alamos, with the kind of software it takes to do these things by putting it in the machine, is also the kind of work we've done. We've always been, until we ran up against Amazon.com, we tended always to have the biggest computer system in the world, or the other weapons labs did, like Livermore, but we were always at the forefront of big machines, and that whole business has changed now. But the human genome became, it's amazingly important, and this is what basic research is. Oh, it's important because, by the way, we can track genetic diseases. There's all kinds of things we can do. You can see what your history of You can track your ancestors nowadays by doing a mouth swipe. They don't do the full genome, but they can do enough of it to work this out. And this is the importance of basic science. You see, you start with Dick Keller, who's simply trying to identify a molecule going by in his system by probing it with lasers, and you end up revolutionizing medicine and biology by being able to measure DNA. This is the nature of how basic research. If we had set out to measure the human genome, I don't know how we would have done it, but we would have made something even more cumbersome. And the value of basic research, and at Los Alamos we're very good at it. Let me make it clear. At Los Alamos, we have a mission to provide safety for the world. We want to have a credible nuclear stockpile. We also help in making nuclear reactors safe and making better fuels. But because we are a multidisciplinary national laboratory, we can do a better job on our mission, and incidentally we have the freedom to explore these other subjects that lead to other things. And this makes the security of the country safer because we're a multidisciplinary lab, and it makes the quality of life better for Americans because we're also doing these things on basic research. And this is the strength of a laboratory like Los Alamos, and I hope it continues to be strong. I mean, I love the laboratory. I've spent well over half my life there, and I don't always like all of the managers at the laboratory, but as an institution, it is a fantastic place to work and has always been. So,
can you talk about kind of the origins of this multidisciplinary approach that occurred in the Manhattan Project?
I don't mean to be too chauvinistic, but Los Alamos during the Manhattan Project had the job that required the most creativity. We had to deal, for example, with how we would make a weapon out of plutonium-239 because we had to compress it. We had the best of the scientists. When we need, you see, the first reactor was at the University of Chicago, their job. Even Ames Laboratory in Ames, Iowa, had a job to do having to do with uranium and how to produce the metal and the production. But these other places had particular jobs. But we had the best of the intellectual horsepower. Mind you, that was also at MIT on completely different subjects. Like I. Rabi was working on radar at MIT, but he would come to Los Alamos. Indeed, he was here in October 1944 when it was announced that he got the Nobel Prize in Physics, and they stopped working on their blackboards and opened a bottle of champagne, drank some, and they went back to the blackboards after they drank the champagne. But the point is, we were the intellectual center. That we had the broadest minds. We had more people go back to their universities after the war than the other laboratories. But these were people, just as Edward Teller couldn't help but think about the hydrogen bomb, the next weapon, even though we were working on the atomic bomb. We had people who were wondering about the biological effects. We had people who looked at the weapons work we were doing at Los Alamos from every possible point of view you see, and how it might affect society. And that they had meetings even when Oppenheimer was still here. He was still here in October 1945, and they were starting to worry about having meetings to discuss the effects on society and things like that. And in that sense, we were the intellectual center, and I believe that's what we did, all of that stuff, and the laboratory hung on to the multidisciplinary nature that we had begun. And in my mind, historically, that's why we were the best of the laboratories. I mean, the work they did at the other ones was truly amazing, and they worked very hard. But Los Alamos had we had more of the Nobel Prizes at our lab, for example, that came later. I have a couple other modern things beside the genome. That we're doing things with ultrasound. just as you image body parts with ultrasonic, something physicists developed as we CAT scans, computer X-ray tomography was also developed by physicists, not at the Los Alamos. This imaging was not done at Los Alamos. But we have people doing ultrasound, and we have two interesting things. Another person also doing ultrasonics who has done some rather clever work by taking a cube and putting it between transducers. He can measure properties of things, including plutonium and lots of other metals. This is rather impressive work on things like getting Young modulus and elastic constants for all kinds of materials. There's Albert Migliore, who's also almost my age. But you can use ultrasonics to study things like, are bridges and buildings going to fall apart? You can do visual inspection on a bridge to look for corrosion, but you also might be able to put some vibrations into it and learn a bit about it. And there was a bridge in Albuquerque over the Rio Grande that was going to be cut down. It was going to be disassembled, and Albert got, at the time, Senator Pete Domenici to get the authority and a little bit of money so that Albert instrumented this bridge. And then they had a physicist down in Albuquerque telling the guys which beams to cut, and he would cut through the beams one at a time and then follow the bridge as it deteriorated and finally fell down so that he could get data on a bridge that was collapsing slowly. And he spent a few days cutting the bridge apart. And it's just interesting that while instead of, you see buildings blown up on television all the time, and by the way, they're using shaped charges, and shaped charges were a product of the Manhattan Project. But here in slow motion, we got to take a bridge apart and study what properties a bridge had when it really was in deep trouble. So instead of using explosive, doing it slowly and monitoring these with ultrasonics. And Albert's work is quite impressive on that.
That's great. Can you, part of what we're trying to do is also educate people. Could you just explain the shaped charges just a little bit? I mean, these are the lenses around the plutonium core and how that works and what a shape,
How does a shaped charge work? Usually, if you have an explosive, you put a thing on it, a detonator. You can probably do that with a bullet, or you can put in a small piece of wire and put a huge voltage on it, like a 3/1000th of an inch gold wire. If you put 20,000 volts on it, it explodes and will set off explosives. And when you do that, it propagates outward, like drops of water in a pond. That's how things go. So how do I take something that looks like a rock making rings irradiate from that point? How do I in fact make the rings come together and focus on a point? The thing we need to do is to have a different velocity. It's how a lens works optically. If you have a lens and you have light coming from the sun, what happens with a curved lens is that the velocity of light is slower inside the lens, and you imagine that you had a little thing coming in here, and this part of the wave hits the glass first, and this one goes faster, and it points it towards the middle. That's how a lens steers light. And we have explosives that have different velocities of shock wave velocities. So the one way you do that is to make it heavier. If you just take an explosive, a regular explosive, and put something like barium in it, it doesn't participate in the explosion, but it's a very heavy atom. And so if I just put heavy atoms, you see, you could use gold or something. Barium is much cheaper, but there are cheap heavy atoms. You load an explosive so that when the explosive, if it was coming out in a ring, what you do is you put a curved shape like a lens. I curve it the other way. I have it so that the rings coming out from an explosion hit a peak of a high density thing, it slows it down and it gives the other ones more time to catch up as it curves. And I can make it into a plane wave. And that's how I can make a plane wave is a flat explosion moving through explosives. If I then made another interface, it'd have to be this way, so that the first stuff out, it's going slowly. I want the stuff so that the higher velocity coming out on the edges comes in and tips it forward, I then can focus those waves by going from a high density thing through a lens, and I can make all the explosives arrive at a point, and that's how you do a compression. But again, we use shaped charges. And when we demolish buildings and stadia in the United States, we use shaped charges on the steel beams. And every now and then it doesn't work real well, because the people were Migliore studied his bridge and cutting what beams made it fall down. You don't always get, every now and then they try to blow up a building and they miss, but most of the time they use overkill. And they use shaped charges because that way you can get the steel beam without making a big explosion. The point is that, again, it's the word focus. I can focus the explosive power onto one particular thing, like a steel beam, make it disintegrate and fall down without having explosive running up, big, huge explosions that would affect the neighborhood. And that's so modern. That's what shaped charges are used for.
So just if you could say a sort of summary statement about the shaped charges were first used in the Manhattan Project, something like that.
Well, it only ran for 2 years. There was a TV show called Manhattan, about the Manhattan Project, and they canceled. It did a pretty good viewership considering it was started in the summer a couple of years ago, and they filmed it near here. Oh, well, the strange thing about that show was that Los Alamos is up on a mountaintop, and it's obvious you're on a mountaintop if you're there, and this was filmed down in a valley, and so it always looked funny to the people who knew Los Alamos that they were down in a valley because we were up on mesas. The terrain looked strange. But that highlighted the fact that there was great controversy of whether it was possible to make a shaped charge. I would say at least over half of the people during the Manhattan Project considered this impossible. In retrospect, it seems obvious, and the analogy with lenses and light waves is clear. But this really was a tricky business. I mean, I've used some of these things to make high fields, and I've had explosive lenses. If you put electric current in a loop and then you compress the loop, the magnetic field goes up. And so the same kind of technology that you use, I can make super high magnetic fields, and I've done this about 80 times. I've had these explosions set off, where if I have electricity running around in a copper ring and I set it in with a compressive explosive, it's called that the magnetic flux is preserved. It can't get past the copper. It's also true that if I have a copper, it would die out in milliseconds, but this is a microsecond explosion. So I put a copper running through a ring. It would run down in milliseconds. However, I set off explosions to compress it. The current goes higher and higher during this explosion, and you get record high magnetic fields, thousands of Tesla. The Earth's field is these are the highest fields you can make on Earth, is by these explosions we do at Los Alamos. Anyway, some of the time we tried using explosive lenses to make a two-stage thing, to compress one and then have another ring inside. And I've lifted these explosives, and the heavier one is brown from the barium in them. And it's true that if I drop it, I would die. And I set it up onto these pieces of metal. And it's an interesting thought, though, that they had me move it, but the technician standing there would say, "Don't drop it." But they were standing there with me. Oh, but it was also true that I didn't get it on quite straight, and there were burrs on the metal. And what I didn't know was that if I slid it, is it okay to slide this stuff over a piece of copper with a jagged edge? I didn't know if that might set it off or not, but I lifted it and sent it, and I got it centered, and we just eyeballed it by looking. But anyway, it's a funny feeling to think, gee, if I drop this, I'm gone. Anyway, because they're loaded, because they're lenses, this one was about this big in this thing. It was surprisingly heavy. It was several pounds. So.
Well, and a related question to explore would be the innovations they used to get the detonators that were attached to these lenses. I think, was it 32 something like that, to all go off at the same microsecond. So it's a very difficult challenge they faced, given the technology of the time. So maybe you can talk about that.
Oh. No, I've seen these. We have, in the bunkers where I was making high magnetic fields, we had the timing devices left from those days. The most important point was, as I said, if a detonator is, say, a 3,000th very thin piece of gold wire that you put 20 kilovolts on it, the way you do the timing is to make sure the cables are all the same length. I mean, it is the speed of light, but you can delay. If I made a really long cable running to one of them, and so what they had was that they had this thing where you put the voltage into the center and the connections were the same length to feed around to the back of this copper thing. And then you made sure the cables were the same length to go to each of the bits of explosive on the outside of it. That reminds me, there was my PhD from Brown University from 1974 is signed by a guy named Don Hornig. And he was here during the Manhattan Project, and he was the guy who sat up in the tower with the first atomic bomb during an electrical storm of the night. And I had never met him, but he had signed my diploma. I didn't walk at graduation. I was already working at the lab, and I didn't. Walking is not a big deal. But I ran into him, and I used to tell people, the guy who spent the night with the first atomic bomb signed my diploma, and then people would say, well, why do you? So anyway, there was, in Atlanta in 1999, was the 100th anniversary of the founding of the American Physical Society, and there was a reception where I was wearing a tuxedo, and I ran into Don Hornig and his wife. And he was wearing a tuxedo, and his wife was in a wheelchair, but she was dressed incredibly elegantly with this shiny dark blue and black dress, and she looked terrific, but she was in a wheelchair, and I had no idea why she was in a wheelchair. Anyway, I go up to Don Hornig, and his wife Lily is in a wheelchair, and she was dressed incredibly elegantly. I mean, in blue and black. But anyway, the two of them are there, and we're right by a table. And then I'm good at making like this sort of boring small talk. I like to do this and then drop something on him. So I said, oh, Don Hornig, you signed my diploma at Brown University when I got my PhD in physics in 1974. He's going, yeah, I was president, you know. And then I go, and then I got a job at Los Alamos, and I've been there ever since. And he's being polite, okay, what? So, and then I tell everybody that the guy who spent the night with the first atomic bomb signed my diploma. And I said, and they always say, well, why did he do that? And then I say, what I always tell them is that you were a chemist and didn't know what would happen. And then he starts laughing. And then his wife starts laughing. I wasn't sure if she'd had a stroke or anything else, but boy, was she rocking that wheelchair. I mean, the two of them were just, it took them a good 10 seconds to stop laughing. And then he said, well, I suppose I better tell you the story. And by the way, I don't read. My wife reads books much more than I don't like to read all that much. And I believe the story has been written down. But I got to hear it from him. And he said that Oppenheimer was afraid that someone would climb up in the tower at night and sabotage it. And by the way, you can't sabotage it by disconnecting a couple wires, because there are tests. You check continuity to make sure nothing's been disconnected. There are a lot of tests you do before you set off an explosion. But somebody advanced enough could have done something. I won't speculate on how to do that. The point was, Oppenheimer only trusted 2 or 3 people completely not to sabotage, and he wanted someone up in the tower. That was in that Manhattan show too. There was a fight up in the tower, as I recall. It seemed a little crazy. But anyway, so Don Hornig, anyway, Oppenheimer trusted him, and he asked him to do it, and that's why he did it. So, but I still liked the way I made the woman in her wheelchair laugh so much.
That's great. That's great. They'll love this. They'll love this. let's see, where have we gotten to next? Can you talk about the water boiler reactor or the developments in the early reactors at Los Alamos and how that laid the way, I mean, what they did, what were they used for?
When U-235 fissions, that is to say a neutron hits it and makes a fission, you on the average get about 3 extra neutrons. It's probably just below, because it depends on which it fissions into. It fissions into 2 not usually identical pieces of lighter nuclei, which by the way are mostly beta emitters and decay. And this is the chain reaction. It turns out that when that neutron comes out from the fission, it's going too fast to fission another U-235 and you have to slow it down. And what they used at Stagg Field was graphite. And anyway, the graphite is carbon. Ideally, you transfer the most energy to another particle if it's the same mass. So if I want to slow a neutron down, the most perfect thing is a water molecule, because it's only a proton. And the neutron, because it has no charge, penetrates the electrons. It can bounce off the proton in water. But I'm not sure why they chose graphite, because its mass is around 12. It's not as good as a lighter molecule. It also was quite dirty. They were all black from handling the graphite and piling it. They were amazingly dirty. In the building I'm building now, we machine graphite, and it's true that you should see how dirty the guys are when they machine graphite. It gets all over and it's slippery. That's why you lubricate blocks with graphite. It was more obvious that you should moderate a reactor with water than with graphite. And it also had the ability, it's easier to handle. Instead of having to stack it up, you can just put a pipe and fill something with water. It needs to be fairly pure. It also turns out that water, though, there's a reasonable chance that the neutron will stick to the proton. There's a reasonable cross-section that a neutron hitting a water molecule, a single proton, will make the water molecule into a deuteron. And whereas a proton hitting a deuteron will not make it into a triton, won't make it into tritium. And the problem is this loss, because you're using water, makes water not such a good moderator. I can't take, as they did in Stagg Field, regular uranium, natural uranium, and moderate it with water. Enough of the neutrons will stick to the protons in the moderator that it doesn't work. So to make a simple reactor, I have to have slightly enriched fuel, something that Russia and the United States can do because we enrich it a lot to make weapons. We have slightly enriched fuel, and then we can use regular water, or you can take standard natural uranium and use heavy water, which is, for example, the Canadians. The CAN-DU stands for Canadian Deuterium Uranium. I think that's what it stands for. They make a heavy water reactor. But anyway, I believe that the first water-moderated reactor was built at Los Alamos. In time, there was one down in the canyon called Omega West, but there was another one. I can talk a bit about looking for nuclear explosions and looking for clandestine special nuclear material coming to the United States. Indeed, it's my son works on the satellites. He got his PhD at University of Colorado in Boulder, but he did his research at the lab and he studied lightning. And it turns out that lightning is very similar to nuclear explosion. There's a bit of energy. He worked in the shortwave radio. If you just like lenses curve light, and explosives can be curved by different density explosives. There's a band of frequency where the radio waves are curved around the Earth, and that's shortwave radio, and roughly that's 2 to 80 megahertz frequencies, and that's shortwave band, and so that we can listen to radio stations on the other side of the Earth. It doesn't go straight. It curves for the same reason that light, the atmosphere lenses it. And my son worked on this, and so he could from Los Alamos with the right antennae, he could track lightning around the world, and he did his master's and PhD on lightning. And we put up satellites. Sterling Colgate suggested the first satellite, the BLS satellites, for monitoring for nuclear explosions. That was negotiated in the 50s in Geneva. Eisenhower sent a team from State Department to do arms reduction negotiation with the Soviets, and it was the first time the State Department took scientists along. One of them was the father of a friend of mine, James B. Fisk, was president of Bell Labs, and he led the delegation. And one of the scientists from Los Alamos was a guy named Sterling Colgate, who in time explained how supernovae work, and he went along. And during these negotiations and months in Geneva, Sterling realized that we could put up satellites that would detect the pulses from nuclear explosions. And that's a whole story. And these things led to tracking lightning, because such satellites would also track lightning. And by the way, there are thousands of lightning strikes an hour around the world, and you have to learn how to tell lightning from nuclear explosions. And my son worked on that for his degrees. And now in our global positioning satellites, we have a 250-pound package that looks at that frequency range shortwave, even though it doesn't have to curve. Our global positioning satellites are watching for nuclear events. We also look for them with that we've always known about, that the earthquake detection thing can spot nuclear explosions. And indeed, natural earthquakes and nuclear explosions allow us to learn a lot about this is the trade-off. If you're doing nuclear weapons and you want to know what the energy of a nuclear explosion was on another continent that somebody else set off, we want to study how the waves turn. And by the way, the waves through the Earth are curved by the varying density, just like focusing light and focusing radio waves. And we can study what's in the Earth by watching how energy comes from other parts of the world. And last week there was a talk by a lady from Berkeley on these subjects. But the point is that we watch electromagnetically for nuclear explosions, for the pulse that comes from them. We also watch with seismology for pulses coming through the Earth. Now, regarding stuff coming into the country, in order to be a low temperature physicist, to cool things, plutonium to a tenth of a degree, there are two isotopes of helium. I need them both. Helium-3 and helium-4. Helium-4 has 2 protons and 2 neutrons, and the nucleus helium-3 has only 1 neutron. And that is what tritium decays into. Remember, there's hydrogen deuterium with 1 neutron. Tritium, or a triton, if it's a molecule, has 2 neutrons. One of the neutrons converts into a proton, giving you helium-3. And helium-3 and helium-4 are very different. Helium-3 is useful for getting to really low temperatures. I'm not going to explain this because it's a fermion, and helium-4 is a boson. And if I mix the liquids at low temperature, I get powerful cooling. And people working at low temperatures use a lot of helium-3, and it had gotten cheap because old hydrogen for hydrogen bombs turned into helium-3, and physicists were glad to have it. But it also turns out that if I want to detect neutrons at a port of entry in the United States, because somebody's smuggling in uranium-235 or plutonium-239, I want to detect the neutrons. And helium-3 was at the time the best way to detect neutrons. I put a cylinder of it, an electrode in, and put a voltage on it. If a neutron comes in and hits a helium-3, it makes a charged particle, and I get a pulse across the voltage in this tube, and I say, I found neutrons. I can array them around and then begin to map out what pattern I have. And so all of a sudden, Homeland Security, since 9/11, 2001, took all the helium-3 in the United States. It's in great short supply, because we put it all at the ports of entry. The United States is working very hard to look at nuclear materials coming in. And Los Alamos, and indeed I even have a patent on using other things, and mine is for lithium-6, for other ways to detect uranium and plutonium coming in by ships or by other ways. There was muon imaging. I also have that in my magazine. Muons, there are something like 1 million muons coming from cosmic rays, they have a lifetime of around 2.2 microseconds. They're charged either positive or minus. And there's like 1 million of them, is that a second or a minute, coming through us every meter. There are these particles coming, they're weakly interacting, and they don't dump energy into us, and as cosmic rays goes, these things don't frighten us, but we can use them for imaging, and we've done rather well at Los Alamos. What do we call it? Oh, we call it PRAD. We have a facility now with proton radiation. That's another one. Anyway, there's different ways to use imaging. And right now we have used these muons to look at one of the great pyramids in Egypt. And right now Los Alamos is setting up to image what the core looks like in Fukushima in Japan. Because, by the way, even though they're cosmic rays and they're coming down, some of them have collisions and go horizontal. And you have to do it coincidence. You have to have a detector that saw them, and then you have to see it go by inside later. So you have to have an incident detector and an exit detector, and we're putting those. The lab is doing it. I don't know if they've started yet, but we're going to image the core in Fukushima, and we've looked for empty rooms on the pyramids. And it's also true that we can do a reasonable job on inspecting containers that come in from other countries on these ships, that without irradiating it, we're not doing anything. We just take the natural radiation that's raining down on the Earth, and in a minute or two we can see if something is very heavy inside, which is what you'd get if you had enough uranium or plutonium to make a weapon out of. And that is also something we're doing besides the neutron detection. So, and again, we've done this image. It's interesting. This imaging that we do, we can do simulated weapons tests with this imaging, with PRAD, and with doing these things. But there we are in the pyramids in Egypt, and we are in Fukushima, and now we're going to deal with Homeland Security. And it's once again that you can't, when we begin to see whether we can image with muons raining down from space, we can't know what benefit it can have to society or what benefit it may have for the security of the United States. And what I claim is that the best way for this country to do this is to fund multidisciplinary laboratories like Los Alamos, and to give us the mission of all of these things. That's what this country needs.
Why is science a double-edged sword? And should we be afraid of science? And
I've never thought about that. Here's something I've not thought about: is science a double-edged sword? Just as fission, we can make nuclear bombs and nuclear reactors, and I can argue that nuclear reactors can be made very safely. But is all science a double-edged sword? If we know a lot about biology, I can't remember, there are various toxins, or bacteria in our environment, I can't remember the names, that can be weaponized and have been. I mean, that our ability to modify bacteria and viruses, we can use this to cure disease, and other people can use these to make them into weapons. I mean, smallpox is a terrible, I mean, it's first contagious when you don't know it is, and then once you have the pustules, it becomes contagious again, so you can spread it around before you're sick, and then when you're taking care of people. It's a terrible disease, and yet we've pretty much taken care of it. But there are I believe that there are bits of smallpox left on Earth, and now we've stopped vaccinating people. But you see that most things that we can do, we can find bad uses and we can find good uses, and I said, this is something people talk about. I guess the most important thing about science is that science is not inherently good or bad. What I do know about science is that it's endlessly fascinating, and it's intellectually wonderful to study it. But you need to realize that it's so many things that humans do. We can go after evil and we can go after good. And don't blame science, and don't blame people for being curious about how things work. And and it's not for me to make these decisions. I love science, and I love doing it, and I love understanding how nature works. I explain to people, if I have a hobby, the one thing I do is I garden a lot. I like gardening. And I think that it's the contrast of what I do at work. I go to work and I have toxic things, radioactive things. I make high magnetic fields, sometimes with explosive. I make really high pressures. I go to very low temperatures. I do things at very high temperatures. I feel like at work I'm fighting nature. And then when I go home and I plant bulbs and I plant seeds, and then I wait, and then nature gives me something beautiful. And I think that the reason I like gardening is that I like the contrast, because sometimes I can fight nature and conquer it and make new things and do exciting stuff, and the other time I can just sit and relax and enjoy the nature. I very much like that contrast. I haven't talked about Edward Teller.
Yeah.
Okay. There was a 40th anniversary reunion at Los Alamos in, I believe, April 1983. And a friend of mine and I, Nicky Cooper, crashed the reception on Friday night at the lodge. And there were eight or nine Nobel laureates there. And I saw people walk up to I saw Edward Teller walk up to people I hadn't seen for a long time, put his hand out to shake hands with them, and I saw them turn around and walk away. And this was because Edward Teller had testified against Oppenheimer and cost him his clearance in the 50s. By the way, the proceedings of those things are available online now and can be downloaded. I've downloaded them but haven't read them. I saw this. I was leaving town at the end of that meeting, and a guy came out with I.I. Robbie and his wife. I.I. Robbie is the one who got the Nobel Prize during the Manhattan Project in October 1944, where they stopped working briefly, had some champagne, and went back to work. And he and his wife came out to a little airport in Los Alamos, and the guy didn't want to stay around. He asked if I would watch over them and get them to their plane, because you had to wait. So I ended up spending an hour with Robbie and his wife. And I don't know how I got it, but I got him talking about him getting old. I think he was thinking about getting old. But I opened it up, and his mind was fine. I had heard him speak. He was the one who argued for the first national lab after the Manhattan Project. He was arguing in 1947 to build Brookhaven National Lab because the country needed accelerators. He was an advisor to presidents through the 50s and 60s. He sat on committees. He's done all these things, and he says, now I still live in Colombia. And he really said this, I don't get any respect. Sounds like Rodney. He said the only respect I get is 2 times a week, Helen and I, we go to the Chinese restaurant by our apartment. And when I go in, the guy calls me Grandpa. And he says, that's the only respect I get anymore in life. And I once was advisor to presidents, and now this is what I get. Okay, I get him down, I put him in line on an American flight to Chicago, and I go into a TWA flight because I'm going to Florida, and I'm changing somewhere else. And I look at the line where I put Robbie in. It was a long line. The lines used to be quite long. And then I looked, and there's Edward Teller, whom I didn't know, and he's pacing. He's pacing. It's just his nature. He's just walking back and forth. And I'm looking, and then here's Robbie and his wife, and they're cute and serene, and here's this guy Teller, you know. And so then I told people about this, and it turned out that these things were written up, and that in December 1983 there was an article about that reunion, and the person writing the article was on the plane to Chicago with Teller and Robbie, and said that halfway through the flight, I read this in the Atlantic. The Atlantic? Yeah. No, Harper's. It was in Harper's, December 9th. I have a copy of it now. And that
apparently Teller, who had just had people not responding to him, and he hadn't spoken to Robbie, according to the writer, Teller walked back and they chatted briefly. Teller stood in the aisle and they talked. And I believe it says that they did shake hands. But okay, so this is Edward Teller, he's famous. In the fall of 1986, superconductivity, the zero resistance, a phenomena we value for magnetic resonance imaging now. We call it MRIs and things, when you're in a superconducting magnet. I mean, it's a fairly useful technology, still is very promising. That's what I spent most of my life working on. Superconductivity was discovered above nitrogen temperature around Christmas in 1986, maybe it was January. And Edward Teller didn't know anything about superconductivity. He's a fine physicist. He was much more of a problem solver than an original thinker. If you get a PhD in chemistry at Caltech, one of the questions you might get on your oral exam is to name the 12 effects in chemistry named after Teller and explain them. There's the ones I know are Jan Teller and Ledane Sachs Teller, but in chemistry, he was a great problem solver, much more than a guy who would invent quantum mechanics. He was the kind of guy who could take quantum mechanics and use it to solve a lot of really useful problems. We're all different when we all have our strengths and weaknesses. But anyway, Teller wanted to understand superconductivity. And he looked around Livermore and Los Alamos and talked to people who knew superconductivity early that year, and he picked me to teach him. And that meant that, and Sig Hecker had been new director then, and he was starting to have Edward hang around a lot. And by the way, if Sig was having Teller at his house for dinner, he would always invite me because Teller made Sig nervous. Teller could be quite forceful. And Sig, whenever Teller was at the house, Sig always wanted me there because I could keep him under control. But anyway, whenever Sig was in town, I would spend 1 to 2 hours a day with him, and I spent over 100 hours. And we became friends because if you think about it, I was probably his last teacher. Now, I don't know the equations in theory. I know roughly what they're about. And that was good enough for Teller. I could explain the phenomenology and the physical properties of stuff and explain roughly what kind of math they did for the theories, and then he could see the rest of the way through. And in time, in the beginning, he kept reinventing the Jan Teller effect. He kept trying to figure out why the high temperatures, why they were superconducting above liquid nitrogen temperature. And it was probably around the summer, somewhere around 94 or so, he finally had made enough progress. I was the editor of the oldest scientific journal at the time, Philosophical Magazine, and Edward finally had a good enough story that I told him I wanted to publish it and I wanted him to write it up. And then I went off for a while and he had a stroke and he forgot that work, and I also can't remember it. And so, but anyway, so he became my friend, and he was the kind of guy, somebody who was giving him a ride, he had people watch over him. I got to make 2 points. He did not understand human behavior once. And I believe that Robert Oppenheimer, who was a very complicated human, frightened Edward. But he didn't understand Oppenheimer. Oppenheimer was a master of human nature. He was charming. He had all of these things, and these were things that Teller was a great storyteller. The children loved hearing his stories. I can talk about that briefly. But he didn't understand human nature, and I believe that Oppenheimer frightened him because he couldn't see what he was doing. He couldn't see that he was a good man. Rather, he simply couldn't see what was going on. The other thing about Teller is that he was such a good storyteller that in time he forgot things. That what he remembered was the story that he had told it. When my wife once asked him about Oppenheimer, and what she got back was like a recording of what you could have read about why he testified against him. his memory were his stories, not the events anymore. And I could see this because as I was teaching him science, he once asked me what I did. And I said I was using explosives to make high magnetic fields and the effects of high magnetic fields on metals. And then he said, oh, I remember. And I think it was Heisenberg, but he was with his advisor in Germany. And his advisor, Edward, was in his 20s. Lev Landau was there, and they were arguing about whether the magnetic field, when you put a magnetic field on a metal, does the field get bigger or smaller inside a metal? Is it paramagnetic getting bigger or diamagnetic getting smaller? Now, when Edward's telling me this story, I'm going, I remember Landau diamagnetism from my books, and there was no, so I knew the answer. There was Landau had it right, but these two guys are arguing. But here's Edward. He hadn't thought about this for 40 or 50 years. You see, I reminded him of a story, and when he was remembering and telling a story that hadn't crossed his mind, that had never gelled in his head, he also was fun to listen to, but I could tell the difference between one he had told many times and one he was thinking of. And in time, these two famous guys said to Edward, you work this out and tell us the answer. And anyway, it was Landau that was right, and Edward explained to me that he thought of a way with a magnetic field, a thing bouncing around the outside of a metal, and that it was diamagnetic. And then he said, and that was the second paper I published. At the time I went to the library and looked it up, but then it was in German, because he spoke German. But the point is that Teller didn't understand human nature, and you couldn't ask him about Oppenheimer anymore either, because he didn't remember his motivations. When he wrote his memoirs, all he could remember was the stories he told many times. And I liked the fact that I could now and then pull up some memory from him that he hadn't thought about, and it was fun, and I could tell the difference. But he was amazingly charming. Oh wait, I was babysitting him at a conference in Houston in 1988, and there was a press conference. This is storytelling. And it was the summer of '88. Anyway, there's reporters. There's a few reporters. This is, for the most part, they're still using pencil and paper. And they say to Teller, because it's well known that he's conservative and he's Reagan's friend. Oh, Teller always said that Reagan and him weren't as good a friend as everybody thought, but that it was good for Reagan and good for him for people to believe they were good friends. So neither of them argued with it. They said, isn't there a Democrat who you might find acceptable? See, now this is, and I'm watching. So Teller that I can't do voices, he goes, but he says something like, well, yes, there is one man. See, he doesn't say a name. He goes on for minutes. A man who? He makes it into a guessing game. See, if you ask me a question, I answer it. But not Teller. You know, and then after a while, everybody in the room's finally figuring out that it's Al Gore. But he wouldn't say the name. He went on for minutes until everybody in the room had figured out that it was Al Gore. This is charm. This is a natural storyteller who does it. He did this instinctively. And he was charming, and he could bring the crowd along with him. Later, he had a story that he said, what were the 3 disastrous colors of the 20th century? Do I get this? And this was a joke of his well after Gore. And he said, and I didn't agree with this, but he said, brown, red, and green. He had considered that the fascism had been bad for the world, and then that was brown. And communism was bad for the world, and then the green was that he thought that taking care of the environment was bad for the world. He had come to hate Al Gore by the late 90s. And I did read that Teller had taken on, that guy from Cornell who said a million things. What's that guy's name?
What, Carl Sagan?
Yes, Carl Sagan. I believe I read that Carl Sagan and Teller had gotten an argument about it. Carl Sagan, who was a scientist, went out and said a little too strongly that the scientific evidence was clear. And there was a debate, I believe, between Teller and Sagan. Where was I reading this? I was reading this. It's probably in the American Scholar. I don't. There is a question, if you think about it, the environmental work and global warming all came from nuclear winter. The possible effects of overdoing nuclear weapons is related to possibly hurting the environment. And the roots of modern climate calculations go back to the Manhattan Project again and the effects on weapons. And Carl Sagan was so passionate and believed he was right that he came out and said that the calculations and the models were firmer than he had any right to say, and a lot of real scientists got very annoyed with Carl Sagan, and it appears that he got in a debate with Teller, and odds are Teller took him apart on that. That it remains true that the scientific evidence is not in. And because, by the way, as you know in science, you can disprove something, but you usually can't prove something. And climate change is probably correct to the extent that science can ever prove it's true. And we should be taking action on it now. But Edward Teller in the 90s objected very much to environmentalists, and I felt bad for him. But he then had his stroke before we ever talked about it much. But he liked his little joke about brown, red, and green. What was the sin of the Manhattan Project? What sin did the physicists commit? And it wasn't that we had made a terrible weapon that killed tens of thousands of innocent civilians. By the way, my wife's father was in the medical corps, had gone directly from Germany without stopping in the United States to the Pacific. He was a supply sergeant, not a medical doctor, to get ready for the invasion. The people, the American soldiers in the Pacific believed that those atomic bombs were wonderful. And my father-in-law loved that I ended up at Los Alamos and that his daughter ran the warehouse. He was the supermarket manager, understood warehouses. He loved what the job his daughter had. The sin that those physicists committed was not that we had made the weapon. The sin was that they enjoyed it. Because the science was so fantastic. The challenges that they met, they figured out problems, they solved them in a few days. They worked nonstop, they worked round the clock. It was the most exciting period of their lives. They were surrounded by their equals, not equals exactly, it takes all kinds of people to make a team. But it took all of these people working together nonstop, very hard, to do something that worked. Something that changed the world. And this was their sin. To this day, people who think about weapons, who work on weapons at Los Alamos, never think, oh, this kills people. We are horrified when we hear from ordnance people trying to make exotic things that tear flesh. It horrifies we at Los Alamos. At Los Alamos, we're just thinking about big energy things because it's fun to make explosions. The people we believe that if we do a good job, our weapons will never be used. That our job is to make something so horrifying that it will not be used and will save lives. That is how the people at Los Alamos think about their jobs. We never think about killing people, and they didn't think about it in the Manhattan Project. That we love doing science and trying to figure things out, doing experiments to see if it worked, to see how it goes. And then, because most of the time you think of an experiment and you say, I'm going to do this experiment, it'll give me this or this, and I'll understand. Then you do the experiment, it gives you a third possibility. Most of the time when you're doing science, it keeps getting wider. It keeps getting more and more complicated, more spread out. And it's only when you begin to get closure that you're beginning to understand the scope of the problem you have, and that it takes you back to where you were heading. It's just fascinating. I love it. And lots of people love doing that. And that's what we do at Los Alamos.
Yeah, talk about Nick Metropolis and what he did. You can start by just explaining who he was and what he did.
It's true that because about Nick Metropolis, I didn't know him well because he spoke less and less. When they would have a party, like for his 80th party, he would agree to have it only under the condition that he didn't have to speak. He just didn't
talk anymore, and I'm not sure what was wrong. There was a guy named Jim Lauk, a mathematician, who was always taking care of Nick and knew it. But I read in Wikipedia that Nick was among the first 50 people chosen. He was probably at the University of Chicago, and that Oppenheimer had picked him among the first 50, and he was very mathematical. And he also had he was Greek, Nicholas, as you might guess, but he had movie star good looks in those days, and he dressed well, and he knew he had movie star good looks, and he enjoyed that. But he was a fine mathematician, and he was involved in the beginning of computing when they were making Maniacs and ENIACs. That was when I already spoke of him and Paul Stein playing secular chess with the first computer where they removed the bishops. But with computation going, but there was a thing that is called Monte Carlo technique. The original paper, I forget who all of the authors were, and I forget who's the first author, but both Tellers were on there. Edward Teller and his wife Mitzi, but there's something funny about the name. She might have had her maiden name on it, I'm not sure. It may have been an earlier paper, but anyway, at least Edward Teller, Mitzi Teller, Nick Metropolis, and there were probably 5 or 6 authors, had this technique called Monte Carlo. There's a way in mathematics that if you want to calculate an energy of something, you have a mathematical expression. And there's different ways to assemble things. It's a very complicated process, and imagine you had a solid and you wanted to squeeze it in different ways and things like that. And it's too many dimensions to calculate. Even with a modern, amazing computer, it's too complicated. And these people thought of a way to take a random state, just make an average. You've got something that you can control the surface. You just do something, you sample a point, you do something, you sample a point, and you try to get an average. In some sense, it can save thousands of years of computing. It was a way to average something that was too complicated to calculate. And I don't remember, I didn't like what Wikipedia said that Nick had a brother-in-law who liked to gamble or something. I don't know, that's not Nick. Nick's style was that this game of chance, in fact, you must randomly pick things and get them. You pick spots to make an average. And it's in fact rigorous that you not systematically pick spots, because if you did it every other something, it's not random. It must be random. In fact, if you weren't picking truly random starting conditions, your technique won't work. And this chance being so important is where Nick, I think it was Nick, not what Wikipedia said, Nick viewed this as Monte Carlo, the gambling haven in the south of France, although it's its own country. And they called it the Monte Carlo technique. And amazing how important that is in parts of physics, and I don't work in those. But when Nick would always eat lunch with Jim Lauk in the cafeteria at the lab, and I would have visitors, and if they were theorists, I would take them up to meet Nick. I would say, "This is Nick Metropolis." Nick would always shake hands and smile at them, but he wouldn't really speak. And at the time, I wasn't sure Nick was playing with a full game. After he died, Jim Lauk did tell me that Nick's mind was fine. He just was having a great struggle to talk. But it was still true that I introduced many, many people to Nick. One of the things you do, if you have visitors and famous people and you put them together, they start talking and you can't get them apart. And that was why I loved introducing people to Nick, because I would say, this is Nick Metropolis, and they go, oh yeah, I'm so pleased to meet you. And then there would be nothing, and then I would get my visitor back quickly. Nick was a really good guy to introduce to visitors. Never got in a conversation with him.
That's great.
Do you want to maybe talk a little bit about Mitzi Teller?
Mitzi?
Yeah, what she was like, and was she a physicist or mathematician in her own right too?
Teller's wife, Mitzi, she had come to the United States well before he did, probably in the 20s, and gotten a master's degree, I think at Penn State. I think it was not Penn, the Western Pennsylvania University. I think she had a master's degree in geology. And it might have been close to geophysics, but she was somewhat technical in her own regard and somewhat mathematical. And she didn't travel with them that often. But when they would be both at our house, we had two boys and they would never come out. We had company, especially when it was Edward Teller. Well, our neighbors sometimes would look and go, look, there's Edward Teller going into Jim's house. But anyway, we had these dinners and the phone would ring and Mitzi Teller would get tense. And as it rang, she would go, aren't you going to answer that? And I'd say, no, the kids will get it. And the kids usually got it on the third ring. And then Mitzi finally admitted that at her house, the rule was that Edward must not hear the third ring. And it wasn't like, or what? I mean, it was, Edward must not hear the third ring. And Mitzi had to get that phone before the third ring. And it looked like she was have a heart attack when she would hear my phone ring for the third time. And by the way, nobody was calling Teller. And this is when we still had landlines, of course. So, but. In the end, though, she got quite swollen, and Edward got her in a hyperbaric, some sort of thing where you go at 2 or 3 atmospheres in enriched oxygen. Even if she had to answer in a third ring. No, when she was suffering, his passion for her was amazing. So they really loved each other. It was fun to see them together. Most of the time she didn't travel with him. And by the way, she yielded. She let him tell his stories for the most part. She didn't say much. So my wife would get her alone and get to talk to her. So.
And how often did the Tellers come to dinner at your house?
Well, I have a wine log, but it's not on a computer. Anyway, I should count out. I believe that the Tellers came 15 or 20 times. I would always have a wine, but he wouldn't drink wine. Well, I'm not sure about all his medical conditions, but what I knew was that I'd give him a little bit of wine and he would never taste it, but he definitely believed in making a toast. He liked to make toasts, and he would always take a tiny amount of wine when he made a toast. The other thing I had learned from teaching him was he's Hungarian, and Eastern Europeans like sugar cubes. If you put sugar cubes in front of him, he's likely to eat one. Well, he wouldn't drink tea through it because Russians do that. But what I learned with Teller was he was getting fatigued, even though he was probably diabetic, and he probably shouldn't do this, but I would give him this much coffee in a foam cup and put 6 to 8 sugar cubes in it. I mean, enough that it was a saturated solution. And he would sip it and he would get his energy back. Yeah. They were driving cross country when they were at Chicago, and the Tellers and the Fermis. And Teller liked to drive. And they went out and hung around Stanford and stuff. But then when they went down to Caltech, von Karman knew movie stars. And they were going to parties with movie stars. And Fermi couldn't resist. Fermi loved going to this. I never read this in a book. Who told me? Oh, Teller told me. And anyway, it was hard for the other 3 of them to get Fermi to hit the road and go back to Chicago, because every night von Karman would go into parties in Hollywood, and Fermi loved going to these parties. So. But anyway, that was von Karman. One of those 5 famous things. One of their daughters called them the 5 Martians. I mean, Teller, as friends, we were trivial. We were away. I think we were sitting in Albuquerque close to the front doors on the benches. I was probably waiting for someone with a wheelchair. I don't know how you arranged those. But I'm just sitting there with Teller. I mean, we just make small talk, like, hey, it's going to rain, you know. And he said, that lady just said, here I am in Hungarian. I mean, he's pointing to some lady who's, hey, so, and then she's waving and her husband comes over. Well, then just for the hell of it, then I go over to the lady, because she's much older than I am. and obviously Hungarian, and I go, this is Edward Teller. And then they go crazy, these two people. I mean, these two Hungarians, they go, Edward Teller, you know. And he hadn't gone back to Hungary for like 50 years. He got an award around 2000 from the Hungarians, but he had not returned to Hungary from World War II until they brought him back when their government had cleaned it. But this idea, and that he thrived on it. I mean, you understand, you just said, hey, that lady said, hey, here I am in Hungarian, and then I go get her and I bring her over, and then they chat Edward up for a while. I mean, it was just right, day to day. I'd go in his room in the hotel to get his teeth for him, this bridge and stuff. No, we were friends. Oh, and he had told me that anything that I needed done at the lab, feel free to say that he agreed with me.